Welcome to Biochem Doc. Today in this video we are going to discuss about Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. This equation gives the quantitative relationship between pH and buffering action of a mixture of weak acid with its conjugate base. Buffering action of a mixture of weak acid with its conjugate base and the pKa of weak acid. pKa of weak acid. The Henderson-Hasselbalch equation. It is a quantitative relationship between pH, buffering action of a mixture of weak acid with its conjugate base, and pKa. Similarly, it also determines the shape of the titration curve. That is, the shape of the titration curve is of any weak acid is expressed by the Henderson-Hasselbalch equation. Shape of the titration curve of any weak acid is expressed by the Henderson-Hasselbalch equation. Then this equation also useful for restating the expression of the dissociation constant of an acid. Restating the expression of the dissociation constant of an acid. Now consider the dissociation of Ha into H plus and A minus. Consider the dissociation of Ha into H plus and A minus. Now we can write the equation as Ha gives H plus A minus. Ha gives H plus A minus. Now from this equation we can write the dissociation constant of this equation, that is Ka equals concentration of H plus into concentration of A minus by concentration of Ha. That is, the dissociation constant Ka equals concentration of H plus into concentration of A minus by concentration of Ha. That is, the concentration of the products divided by concentration of the reactants. Now we can rearrange this equation. So we get H plus equals Ka into Ha by A minus. So by rearranging the equation of Ka for solving H plus, we get H plus equals Ka into Ha by A minus. Then convert this to logarithmic functions. So we get log H plus equals log Ka plus log Ha by A minus. So we get log H plus equals log Ka plus log Ha by A minus. Now to make the expression negative, multiply this equation with the minus 1. To make the expression negative, multiply this equation with the minus 1. Multiply with the minus 1. So we get minus log H plus equals minus log Ka minus log HA by A minus. As we all know that pH equals minus log H plus. Similarly, pKa equals minus log Ka. Now substitute these values in the above equation. So we get pH equals pKa plus log HA by A minus. pKa minus. pH equals pKa minus log HA by A minus. Now, to remove the negative sign, we want to invert this portion. We want to invert this. So we get pH equals pKa plus log A minus by HA. This is the Henderson-Hasselbalch equation. pH equals pKa plus log A minus by HA. Generally, this equation we can write it as pH equals pKa plus log proton acceptor by proton donor. pH equals pKa plus log proton acceptor by proton donor. This equation has great importance in protonic equilibria. This equation has great importance in protonic equilibria. Protonic equilibria. Now, let us see how it is important in protonic equilibria. How the Henderson-Hasselbalch equation is important in protonic equilibria. Consider the condition where concentration of A minus equals HA. Concentration of A minus equals HA. Or when an acid is exactly half neutralized. An acid is exactly half neutralized. Now, under this condition, we get the equation pH equals pKa plus log A minus by HA, that is equals pKa plus log 1 by 1, that is equals pKa plus 0, that is log 1 by 1 is 0, that is equals pKa, that is pH equals pKa. So at half neutralization, pH equals pKa. So this equation shows why the pK of the weak acid is equal to the pH of the solution at the midpoint of its titration. This equation shows why the pK of a weak acid is equal to pK of the weak acid is equal to pH of a solution at the midpoint of its titration. Now consider another condition. When the ratio of A minus to HA equals 100 to 1, then we get pH equals pKa plus A minus by HA, that is pKa plus log 100 by 1, that is equals pKa plus 2. This means log 100 by 1 equals 2. Log 100 by 1 equals 2. That is, we can write log 100 minus log 1. So log 100 is 2 and log 1 is 0. So we get the answer 2. pKa plus 2. pH equals pKa plus 2. Now we can consider another ratio, that is A to HA ratio is 1 to 10. 1 to 10. So we get pH equals pKa plus log 1 by 10. So pH equals pKa plus log 1 by 10 equals minus 1. Log 1 by 10 equals minus 1, that is log 1 minus log 10. So we get the answer minus 1. This is based on the log m by n. Log m minus log n. Log m by n is log m minus log n. So by using this, we can write it as log 1 by 10 is like log 1 minus log 10. So we get the answer minus 1. So pH equals pKa plus minus 1. So by using the Henderson-Hasselbalch equation at several ratios of A to HA, between the limits 10 raised to 3 to 10 raised to minus 3, between the limits 10 raised to 3 to 10 raised to minus 3, we can describe the titration curve for weak acids. Titration curve for weak acids. So the Henderson-Hasselbalch equation is the quantitative relationship between pH and buffering action of weak acid and its conjugate base and the pK of the weak acids, and it also determines the shape of the titration curve, and it also useful to restating the dissociation constant of weak acids. This is all about the Henderson-Hasselbalch equation. Thank you.